In this video, we're going to talk about boundary work. And generally, boundary work means work done on or by a piston, at least in our context. Normally, work is force times distance. Usually that's what you have in physics, is you have like a force applied and it moves over a certain distance, and then that is equal to work. Now, sometimes you can write this work as, say, force times distance, or force times maybe the change in x, in, say, if you're going along a linear path, or in differential form, you could write it as dw equals f dx, like this. Or if you want to integrate this, then you could integrate both sides and have f dx like this. Now, say in the case of a piston, and so you have, let's say, a piston in a cylinder. And so you have like some kind of pressure. So your system is in here, would be your gas, like this. And again, let's say this could be, maybe this gas is doing work on the piston, or the piston is doing work on the gas. In any case, you have like pressure in here. So it's under pressure, and it's pushing in all directions, the pressure. And so the work, say the boundary work, the differential form is going to be the force. And of course, if you have pressure against the piston, then the force is going to be the pressure times the piston area, like this. Again, that's going to be the force. And then the amount it's going to move, the distance will, say, be dx, like this. Now, we could put these last two factors together. So if you have a dx, this is going to be the differential volume, like this. So then now we can write this as dwb equals p dv, like this. Or wb equals the integral of, say, v1 v2 p dv, like this. So this would be like the work of a piston, either the work done by a piston on the system, on the gas, or the work done by the gas on the piston. So we'll be dealing with this equation quite a bit. So as I said, we'll be working with this integral. And then just to note, this integral represents this area. If you integrate from V1 to V2, that represents the area under the curve between V1 and V2 on a PV diagram, pressure here, volume here. And also, and it does depend on the path. The amount of work depends upon the path. It depends upon the relationship between pressure and volume all the way through the process. So, uh, depending upon the path that you cover, the work can be different. But so doing this integral, you can think of the work being represented by this area under the curve. So we should write that down that work depends on the path, and therefore work is not a property. It's the same with heat. Heat also depends on path. So heat is not a property. Remember, if something is a property, it only depends on the two endpoints. But again, in the case of work, how you get from one to two makes a difference in how much work you use. Same with heat, it also depends on the path. So again, if we go back to our integral, now in order to integrate this, we have to know what P is. We have to know either its value if it's constant, or we need to know the relationship between P and V. So for this need to know this function. So we mainly will look at the several cases. Again, remember we're looking at boundary work for a closed system. And let's look at the cases here. Number one, if the pressure is constant, again, that'd be the case. Remember, that's represented like maybe if you have like some kind of mass here, some kind of weight, keeping the pressure constant. And then, this piston is free to move. And again, your system is going to be this gas in here. And you're going to have some pressure P. Again, as long as this piston's free to move, then that's going to keep this gas here constant. And again, if it's constant, if the pressure is constant, then we can say that this integral, we can pull out the P out of the integral. Like this, and then when we integrate it and put the bounds in, it's going to be simply this. So that's going to be the calculation of work if the pressure is constant. And again, you can see this would be a case here where the pressure is constant. Let's say you're adding heat to this, and this maybe is going to rise, but the pressure will stay constant because this mass up here is keeping it constant. Now, if you want to look at the work done, again, if you look on a PV diagram, and say this is your constant pressure between V1 and V2. Once again, work is just going to be the area of this triangle. And case 2 would be if the volume is constant. But now when you think of this, if you have the volume constant and you're integrating from V1 to V2 PDV, and you integrate this, but let's say these volumes are both the same. Let me just call this V2 equal to V1. Then when you integrate it, of course, uh, this right here will end up being 0. Anytime you have the two bounds exactly the same, the integral has to be 0. Or if you think of it, once again, on a PV diagram, you have your pressure here and your volume here, and it doesn't matter what your pressure is doing, from beginning to end, this volume is always going to be the same. So there's no area under the curve. So that's another way to think of the work being 0. Another case is if the temperature is constant throughout the process and the gas is ideal. So let's say if you have something like this, for an ideal gas, you have PV equals MRT. And again, uh, we're assuming this is a closed system, so this mass has to be constant. And of course, this is always constant. And then also, if the temperature is constant, if we have constant temperature, then we can say that PV is equal to a constant. And let's call this equation 1. And we can rewrite this. We can rearrange this so the pressure divided by both sides by volume. We have this. Or if you want to think of it, again, that right-hand side, sometimes it might be helpful to say, okay, this constant here is going to be this value, MRT over V is another way to think of that. But we'll work with this for the moment. So now think of what we have if you look at our boundary work. When we substitute here, like this, so I'm going to put, for the pressure, I'm going to replace it with what it's equal to, C over V. Again, remember going from V1 to V2. Now we can pull out the constant. And then we have dv over v. And of course, you remember from calculus, this is going to be the log like this. And so it's going to be c. I'll factor out the c, so it's going to be log of v2 minus the log of v1. And you remember we can combine the logs when we have a negative like this. So you can think of this as being work is going to be C log V2 log V1 or log V2 over V1 like this. And again, remember what these are equal to. Our C was our pressure times volume. So we can replace that here. And we can say even P1 V1 if you want to. Or you can say P2 V2 since that quantity is constant. Of course, keep in mind this is, to use this equation, you have to have an ideal gas and constant temperature. And case 4 is the case when you have the pressure and volume related by PV to the N equals C, like this. Again, pressure and volume related by this. Now, N is a polytropic index. We're going to talk about that later, but it's a relation where P and V to the N is equal to C. Now, for the case we just saw, for a constant temperature ideal gas, N is going to be just 1. So that was a special case of this process here. Again, this is called a polytropic process. And again, let's see how we can handle work in the case of polytropic process. PV to the N equals C. Once again, we want to solve for P. Similar to what we had before. And then if you look at your boundary work, remember PdV, V1 to V2. And we can put P into here. So that'll give us C over V to the N. I'll factor out the C like we did previously. So that'll give us uh, dV V to the N from V1 to V2. And then this is going to be like this. So I brought the V up into the numerator so we can integrate properly. Remember, whenever you integrate this, you always add 1 to the exponent. This, and then you have, and then I'm going to put a common denominator. So I'm going to distribute that C. So when we put the bounds in, we have V2, V1, and 1 minus n in the denominator. I'm going to rewrite that, put the 1 first, and that'll be 1 minus n like this. So that's going to be the work in the case of a polytropic process. Next, let's take a look at this example. Uh, 0.35 pounds of nitrogen resides in a piston cylinder device. The initial volume is 1.5 cubic meters. Suppose heat is added such that the volume is increased to 2.25 cubic feet. How much heat has been added during the process? Assume the pressure is constant and assume constant specific heats. So we're starting out with 1.5 cubic feet volume and heat's added to bring it to 2.25 cubic feet. And we need to find the heat added. So again, we don't have anything moving through the system. No, this is a closed system, no change in elevation, etc. So I think we can assume, actually, we can assume very safely that there's no change in kinetic energy, no change in potential energy, and so the equation we're going to use is the first law, Q minus W equals a change in internal energy. Again, if we had had kinetic energy, potential energy, we would add them here. Then uh, also nitrogen is an ideal gas. So we can say that the change in internal energy is mcv delta T. So we're going to use those. And we're going to need to find information about the molecular weight. And if you look in my book, it's table B1. Again, if you're using a different book, you probably have something different. I'm sure you do if you have a different book. That's going to be our molecular weight. And then our R hat, which is the universal gas constant, is 10.73 psi a uh, cubic feet pound mole R. So that means our R which is our R hat over the molecular weight, is going to be uh, this divided by this. And to save some time, I'll just put the answer down. That'll end up being PSI A feet cubed per pound mass. Degrees are like this. Now, we also may want to have it in the other form as well, where we have BTUs. We might find that comes in handy. So we could also use this form. And we divide these out. BTUs per pound mass R. You'll find sometimes when we have our answers, sometimes we want to use this one, sometimes we want to use this one. Now we're going to need to find our temperatures because we're going to need our delta T. So we have P1 V1 over M or T1. So if we solve for T1, that'll be P1 V1 over MR like this. And our pressure was given as 50 psi. Now, uh, let's see. Yes, so we can use this because I think the psi will cancel, so we don't have to convert it. And the volume initially is 1.5 cubic feet, 0.383 psi feet cubed on mass R. Mass like this. And when you put that on your calculator, you get 559.5 Rankine. Now, we have to sort of distinguish here. This Rankine, this R here is Rankine, whereas this was our universal gas constant. So just have to be mindful of those, that those are different. So then we can also solve for T2. And again, the pressure is constant. And the new volume is 2.25. And of course, our mass is not going to change. Oh, by the way, I should have checked on the last one. The units, notice the PSIs cancel and the feet cubed cancel and the pound mass cancel. So we're just left with 1 over R. When we do the reciprocal, we end up with R again, which is temperature Rankine. So put that in your calculator. The temperature is 839 Rankine. And now we're going to have to find the specific heat at constant volume. So we're going to have to uh, use the average temperature to do the two temperature average, which is our 839 plus our 559.5 divided by 2. This gives us about 669.25 degrees Rankine. If we subtract 460, the T average would be 239.25 degree Fahrenheit. And we can use that then to find our CV. And if you look up at the table, it's pretty close to 250. So again, from the table, CV was 1781 BTU per pound mass. Or in my book, this was table B8. And then finally, we can then calculate our change in specific heat. Again, we have 0.35. And our change in temperature was 839 was our T2. 559.5 was our T1. And this is 17.32 BTUs. Now we have to calculate the work. Again, remember the pressure is constant. So the work is just going to be PV2 minus V1. Remember, this is just for constant pressure. And so our work, which again is our boundary work, which is the only work we have, it's going to be 50 psi, pounds per inch squared. But now these are in feet. So we're going to have to convert the 50 psi to feet. So it's going to be 144 square inches for every square foot. And our volume, our second volume is 225. Our initial volume is 1.5. And when you put that in your calculator, you get 5,400 pound-feet. Now, if we change that to BTUs, we have 1 BTU per 778.169 pound-feet. And so that's 6.939 BTUs, like this. Then finally, if we use our first law, Q minus W is delta U. And then, so we have Q equals delta U plus W. And we just found that delta U 17.42. and our work was 6.939. And so our heat that we had to add was 24.39 BTUs. Let's take a look at this problem. Hydrogen is slowly compressed according to the PV to the 1.4 equals a constant. The final temperature is 400 degrees Kelvin. Calculate the work done. And it looks like we're starting with zero point 0.5 kilograms, 120 kPa, and 320 K is the initial. Then the final is the 400 K. And if we look up some values for hydrogen, the R value, again, it's R over the molecular weight is 4.124 kilojoules per kilogram Kelvin, like this. And again, now we're told this relationship here. Now we'll see in a minute that we might also want to rewrite this. We can solve this for the pressure P, and we'll write the constant part with just a C. And so we could divide both sides by V to the 1.4, and that's going to give us C V to the negative 1.4, like this. And again, so this is an isentropic relation. Remember, whenever we have PV to the N equals a constant, and we calculated a little while ago that for an isentropic relation, the work may be calculated this way. Now, one thing, and I didn't derive this separately, but we can sort of derive it here, is that we can actually use this relationship up here a little bit. So let's, first of all, let's put the 1.4 in. And I'm going to put the negative 1.4 here. I'm going to separate the V to the first power. And again, we'll write this as well. We're going to write this as V to the minus 1.4 times V to the first. Like this. And then we'll replace, notice what we have here, CV to the minus 1.4. We'll replace that with P here and replace this with P here. So I'm replacing these quantities. Of course, actually, this is V sub 1 here. So we'll replace this with P2 and this with P1. this. Now, of course, we don't know, let's see, we don't know the final pressure. Now, we know the final temperature, and we could use, let's see, yeah, so we don't have enough information here, but what we do know from the ideal gas law that PV equals MRT. So we'll replace this with MRT. And of course, that's going to be T2. Of course, obviously, the M is the same and the R is the same for both states. And replace PV with MRT. And actually, we could even go one step further. We could factor out the M and the R, can't we? And then the M is the mass, which is 0.5 kilograms. The R was 4.124 kilojoules per kilogram Kelvin. Our temperatures, our final temperature 400, our initial was 320. This and that this becomes negative 412.5. Let's check the units. The kelvins cancel, kilograms cancel, we end up with kilojoules. Negative 412 kilojoules. And of course, think about the units. Uh, joules, that's the unit Newton meters. And of course, Newton meters then would be work. So the total work done is negative 412,500 Newton meters, or negative 412.5 kilojoules. And again, because it's negative, that means the work is done on the system, which makes sense because it's compressed the gas. And the system is going to be the gas, like this.